AP Calculus BC, Unit 6, Day 4, office hours. These are your answers if you need to check them quickly. Hopefully you check them already. Also, don't want you using that formula or that formula in your work. On tests, I will penalize you even if you get it right. If you get it wrong, I'll heavily penalize you. But these answers on 1 and 2 could have been a little different because you're kind of estimating values from these graphs, but maybe ballpark close, especially the k values. Okay, here are the answers number 3 and 4. Check your answers. These don't have any work. Pause the video if you need to. Okay. All right. On to the answers on the back. Pause the video if you need to check these. It's number 6 and 7. 7, 8, 9. These are just the answers. You guys should work. All right, let's try these out. Logistic growth. Okay. So again, you do want to memorize this, and you do want to memorize this. You do not want to memorize or use that. You do want to memorize this. You do not want to memorize that. Those 3 things are sufficient, and I think you have enough to memorize. So first problem, P naught, M, and K. So P naught would just be right here, right? This is your P naught. So P naught is about 2. Carrying capacity would be what it goes towards. That's your carrying capacity right there. So I'd say that's probably about 8. So those are easy. The K value, we want to use the formula. Let's see. So we use our formula right here. Say, okay, well, P is going to equal 8 over 1 plus A E to the negative M K T, right? And let's see, we're trying to find the K value. So let's see, we could use P naught. P naught is 2. And so if we plug 0 in for T, it's going to be e to the 0, which is 1. So we get that. So we could use this to find A. So that's going to be 2 plus 2A equals 8. 2A equals 6. A equals 3. So we'll plug that into our P equation. 1 plus 3E to negative 8 KT. Now here's the deal. We need one other point. So I'm going to go ahead and use this point right here. I'm going to use 2, 4, which I think should be, anyways, the point of max growth rate. But we need any point. So I'm just going to use that point as another known point other than P naught, because that makes all this drop out. So we're going to plug that in, negative 8K times 2. And then we could solve for E, or we could solve for K. So we're going to cross multiply 4 plus 12 e to the negative 16k equals 8, and 12e to the negative 16k equals 4, and e to the negative 16k equals 1/3. And take the natural log of all sides. And then we get k equals negative 1/16 natural log of 1/3. And as a decimal, that is 0.069 or 6.9%. So there you go. It's a little bit of work there. Okay. This is your P naught. Looks like this is your carrying capacity. So I'm going to say P naught is about 400 and M is about 1000. That part's easy. But now we need to find our model. So P equals M, which is 1000 over 1 plus A e to the negative 1000 kt. So we can find A by using P naught, which is 400. And then e to the 0 is just going to be 1. So then we get 400 plus 400A equals 1000. 400A equals 600. A equals 3 halves or 1.5. Okay, then we need any other point. So we could do like half the carrying capacity, maybe is like 100, 500. I mean, that's just an interesting point, but I mean, we could use that. Okay, so we're going to put 500 equals 1000 over 1 plus 3 halves e to the negative 1000 times k times 100. So we just need to solve that for k. So if we multiply this over here, it's going to be 500 plus 750 e to the negative 1 with 5 zeros after it equals 1000. We're going to subtract 500. We're going to divide by 750. So it's going to be 500 over 750 is 2/3. We're going to take the natural log of both sides. And then we're going to divide both sides by negative 1 with 5 zeros after it. So that's your k value. K equals natural log of 2/3 over negative 100,000. As a decimal, that is very small, 4.055 times 10 to the negative 6th, scientific notation. So there you go. A little tedious. Okay. I think those are the worst. Number 3, suppose that the growth is, so they're giving you the growth model. What is the population times 0? So we did some like these in class. Now, the thing that you got to remember is that this needs to be 1, right? So you got to factor a 5 out of everything in the top and the bottom. Okay. And you might even write what you've memorized just to help you out. So the population times 0, actually you don't even need to do any of this. You just say, you just plug 0 in. P naught equals 60 over 5 plus 7 if you plug 0 in for time. And that's 60 over 12 is 5. So that's P naught. The carrying capacity is now 12. The K value, well, we can get that from from this right here. negative 1 equals negative mk, negative 1 equals negative 12k, k equals positive 1/12. All right. When does the population reach half of the carrying capacity, which is also the time when it's the highest growth rate? But that's just easy. That's just some easy algebra there. You're gonna make it half the carrying capacity is 6 instead of equal to the. You could even use the original one if you want. If you don't like that fraction, either way. And we can multiply. This is going to be 30 plus 42 e to the negative t equals 60. So it's going to be 42 over e to the t equals 30. So it's going to be e to the t over 42 equals 1 over 30. Multiply by 42. I lost my negative. Oh, no, I didn't. I got rid of it on purpose. So then we're going to take the natural log of both sides. We could take it was 21 over 15. We could take a 6 out of the 7 over 5 if you want. So there it is. As a decimal, it is 0.336. So that's time. Find the initial value whose solution is. So this is just, you can go through all that work I showed you in the notes yesterday, or you could just use the memorized. So we're trying to find the initial value problem whose solution is this. So we're working backwards. What's the differential equation that this would have been the solution for? It would be dy dt equals kp m minus p. So it's going to be dy dt equals k 1/12 p m 12 minus p. Initial value means you need initial value. Y sub 0 equals, we already wrote it, was 5. So we should put y's in here if it's going to be y. So there you go. Okay, next one. Similar, same kinds of questions. So this one's in nice form already. M over 1 plus a e to the negative mkt. That one's nicely written. So times 0, you're just going to plug 0 into it, and you get 1,000 over 1 plus 999, which would be 1,000 over 1,000, which would be 1. The m value is right there. M equals 1,000. The k value, what we need to do is we have negative mk, and there it is. So it's going to be negative 0.9 equals negative mk. Sorry. Yeah, mk. And m is negative 1,000. So we divide both sides by negative 1,000. And so we get k equals, we could write it as 9 over 10,000. That's the k value. Or 0. For every 10 you divide by, you move the decimal over to the left 1. So it's going to be 1, 2, 3, 4. 1, 2, 3, 4 spots. 1, 2, 3 zeros. All right. When does the solution reach 75% of the carrying capacity? Okay, well, 75% of the carrying capacity, 0.75 m, is going to be 750. And we're going to set it equal to our growth model. And we just need to solve for t. Now, the numbers here are going to get a little ugly. I'll see how far I can take it without using a calculator. Okay, so we're going to get 750. Now, what's 750 times 999? 750 times 999. So 0, 0, 0, 0. 5 times 9 is 45. Carry the 4 to 45 is 49. Carry the 4 to 45 is 49. 0, 0. 7 times 9 is 63. Carry the 6 to 63 is 69. Carry the 6 to 63 is 69. And then that's going to be 0, 5, 12. Carry the 1 to 18 is 19. Carry the 1 to 13 is 14. Carry the 1 to 6 is 7. So that's going to be 749, 250. That's fun. Equals 1,000. So that's going to be 749, 250. Oh, by the way, that's e to the negative 0.9t. And we'll divide both sides by that. And I think we could clean that up a little bit. We'll take the natural log of both sides. How many times does 250 go into that? Oh my gosh. I mean, it's going to work out. I think it should work out kind of nice. 250 goes into 1,000 4 times. So 4 times 749. 36, carry the 3 is 16 is 9, carry the 128 is 29. And then one more. So that'll be 1 over 2997. So t equals, now this is negative 9/10. So I could say it's a negative 10/9 natural log of 1 over 2997. So that's the exact answer. As a we could even clean this up. We could say, oh, well, this is going to be 10/9 times 2997, bring the negative in as an exponent. As a decimal, it's 8.895. So, all right. Cool. Now it says find initial value problem. So we're going to do dp dt equals kp n minus p. So we're going to get dp dt equals k, which, let's see, we found that somewhere. 9 over 1,000 p, and the carrying capacity was 1,000 minus p. With the initial value, p sub 0 equals 1. So that's the initial value problem whose solution is what we started with. I don't know. So, all right. Okay, next one. Similar questions, but I'm giving a differential equation. Now remember, this is supposed to be kp n minus p. So we need to work on this a little bit, I think. There's the p, but this needs to be just a single p. So I think what we need to do is divide a 0.1 out, which is also the same as multiplying that by a 10, multiplying that by a 10, and then dividing that by 10. So it's going to be, I think, 1p. I'm going to put the p over there. That's going to be 10 minus p, right? So there's your k value, and there's your m. So the carrying capacity is 10. The k value is 1. For what value p is the population growing most rapidly? What value p? This is easy. It's half the carrying capacity. And p equals m over 2, 10 over 2. That's the population when it's growing most rapidly. So I didn't ask for the time, I just asked for the population. There you go. And this was logistic, right? These are all logistic so far. Okay, interesting. Okay, that one was nicely easy after our other ones. Okay, got a few more in the back. Okay, so we have another one where I give you the differential equation, but we got to work on it a little bit. So remember, dp dt equals kp n minus p. And so I think we need to factor out a p and yeah, p. Okay. And we need a single p right here. So we need to factor out 0.001 p, I think. 0.001 p. So if you divide that out, it's the same as multiplying by, I think, 1,000. So that's going to be 50,000 now minus p, if we did that right. So here's your k value, and here's your m. So our carrying capacity is 50,000. Our k value is 0.001. And what's the value of p, where it's growing the most rapidly? Well, that's just going to be half the carrying capacity, so 50,000 divided by 2, so that's going to be 25,000 is the p-value where the population is growing most rapidly. All right, okay. Suppose that a college residence hall houses 1,000 students. Following semester break, 20 students in the hall return with the flu. 5 days later, 35 students have the flu. Use a logistic model to set up an initial value problem whose solution is the number of students who will have the flu T days after return from break. Note that the differential equation in this case will involve a constant of proportionality. It's going to be logistic. So what are some of the things that we have here? So it says to write a logistic model. So that's going to be who initial value problem. So it's a differential equation. We're going to have dp dt equals kp n minus p. That's what we're going for. So let's see. And it says there's going to be a constant proportionality, the k value. This 1,000 is our carrying capacity. That's the max students who can do it, right? This is our p naught, and this is just another known time, which we can use to maybe find some unknowns. So for our problem, I think we could say that dp dt equals kp 1,000 minus p, and p0 equals 20. That's our initial value problem. Okay, now B says solve the initial value problem and use the given data to find the constant and proportionality. So we're going to, we also know that P5 equals 35. Okay, so let's see. When I say solve it, I mean we could just use the solution that we've memorized for logistic growth. It's m over 1 plus a e to the negative mkt. We have n, and so we just need to find some of these other things. With p naught, we can find the a value, right? P naught equals 20. So 20 plus 20a equals, m was 1,000. So that's 1,000. So 20a equals 980. You can divide by 20. So a equals 49. So that's one of the things that we need. And now with that, we can plug that in. We have 1,000 over 1 plus 49 e to the negative m is 1,000 kt. So we just need any other point other than times 0 to plug in to find that. So we have this other point that we have 35 when the time is, time is 5. So we're going to solve this for k. So we're going to get 35 plus, we got to figure out what 35 times 49 is. 5 times 9 is 45. Carry the 4 to 20 is 24. 0, 3 times 9 is 27. Carry the 2 to 12 is 14. So it's going to be 5, 11, 7, 17, 15 e to the negative 5,000 k equals 1,000. And then we're going to keep solving. We're going to subtract 35. So we get 1715 e to the negative 5,000 k equals 965. We're going to divide by 1715. 1715. Can we simplify so we can take 5s out? I don't know. I think that's fine. We just leave that. So we take the natural log of both sides and we divide by negative 5,000. We get k equals negative 1 over 5,000 natural log of 965 over 1715. As a decimal, that is 1.150 times 10 to the negative 4th. In scientific notation is 0.000115. So that's the k value, which allows us to finally write our solution. That's the constant proportionality, right? And I guess our solution now is population equals 1,000 over 1 plus 49 e to the. Now, if we multiply this by 1,000, 1, 2, 3, 4. No, actually, 1,000. We just move it 3 times for every 10. And so that's going to be negative 0.115 t. So that's our solution now. It says make a table that illustrates how the flu spreads day to day over a 2-week period. So we could totally just use our calculator to do that. Okay, so on graphing calculator, let's see. I'm going to enter my equation here. Take advantage of the table. 1,000 divided by parentheses 1 plus 49 to the negative 0.115 x, close, close. I'm going to go to table. Oops, no, that's not what I'm going to do. I'm going to go to, I don't know. I thought it was, okay. I think I messed up. Second, insert parentheses. Okay, I think now I'll go to table. I'm going to type in, it says over a 2-week period. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I guess you can only go so far. We could write these values in a table. I think something's wrong. Check. Seems like I typed it incorrect. But if we go to table, it should say 20 time equals 0. So what's wrong with this? This is supposed to be 49. So we're going to insert E to the negative MKT. Okay, so now that should be right. Let's check that out. Okay, that looks better. So I'm going to make a little table here. Time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2 weeks. This is the population. So we got 20. I'm just going to truncate 22, 25, 28, 31, 35. It's so close. 35, 39. We could go type some number on 7, 8, 9, 10, 11, 12, 13. So that's going to be 43, or I don't know, what are we on? 43, 48, 54, 60, 67, 75, 83, and lastly 90, 92. So there we go. And then we could graph it. It says using a graphing utility generate a graph. Okay, let's go to window and say 0 to 14. And we say like -1 to like 100. Graph it. And it looks like this. So we're up to about 100 there. So there you go. Okay. So number 8, you have different equation, P naught. So we're actually trying to solve this. Now, by the way, this is not logistic. It doesn't say it's logistic. It looks really close to logistic. It would be KP M minus P. So this right here is not logistic. So we're just going to solve this. So we're going to separate the variables. So we're going to get a dP over P. I'm going to leave everything else, I think. I don't know, I'll bring the 3 over here. Why not? And then this is going to be 1 minus T over 4 dt. So we separate the variables, and then we integrate both sides. This is going to be T minus T squared over 8 plus C. We have initial condition. Let's go ahead and find it. Natural log of 2, absolute value of 2. We're going to plug zeros in for the T's. So C equals 3 natural log of 2. All right, so we're going to plug it back in. So we have 3 natural log of the absolute value P equals T minus T squared over 8 plus 3 natural log of 2. We're going to divide everything by 3. We're going to, let's see, what do we get? 1/3 T minus 1/24 T squared plus natural log of 2. We're going to exponentiate both sides. We're going to get rid of, I'm going to use rules of exponents and break this up a little bit to get that guy as a 2 in front. And then we should figure out if it's positive or negative. It's got to be positive. So our solution is finally PT equals 2 e to the 1/3 T minus 1/24 T squared. The domain for the domain, what is the domain going to be? Let's see, the domain, no issues here, no issues there, so the domain should be negative infinity, positive infinity. All right, okay. One more to go. One more to go. Carrying capacity. So find the carrying capacity. Oh, this should be a nice one. We want to get Kp n minus P. So we need a single P here. So we got to factor that out. It's going to be 0.012 P. And then what is 6 divided by 0.012? Well, let's see. I'm trying to pull this off without a calculator. So I'm going to move this over 1, 2, 3 spots. I'll move this over 1, 2, 3 spots. And so 12 goes into 65 times. And so that's going to be 60. And then you got 2 more zeros there, right? So 500 minus P. So that's your K, that's your M. So your carrying capacity is 500. There you go. Okay, that's it. Logistic growth.